In section 5 of chapter 12 here, we're going to be talking about tangent segments. And before we talk about tangent segments, let's just take a look at a class starter problem. And this class starter problem deals with chords, and specifically a diameter that is perpendicular to a chord. Recall that we learned in an earlier section in this chapter that a diameter perpendicular to a chord bisects the chord and its arc. So the fact that we have this right angle here actually tells us that these two pieces, FH and DH, are congruent, and also arc FG and arc DG are congruent. Now they actually ask us to find the radius of this circle. So they've given us D to F. D to F was given to be 30. But since the two pieces HF and HD are congruent, we could conclude then that H to F is 15. So that piece right there is 15. And then they also told us that C to H was 8. C to H was 8. That was given to us. So that's telling us that this piece right here is 8. If I then draw in a radius, and I'm going to draw in the radius from C to F, I have a right triangle. So we can use the Pythagorean theorem. We're looking for that radius. I'm going to call it x. So x squared would equal 15 squared plus 8 squared. Now, when we work out 15 squared plus 8 squared, we get 289. Drawing on our algebra, we know that we solve this using square roots, and we actually come up with two possible answers, x equals 17 and x equals negative 17. However, this one does not apply in this problem because radii, a radius, cannot be negative. So the only answer to this problem is 17. And again, in this chapter, it is imperative you must box your answers, or it is wrong, because we'll take it to mean that it's an extraneous solution. Okay, let's take a look at a tangent segment. Now, recall that a tangent segment touches a circle at exactly one point. And a tangent is perpendicular to the radius at its outer end point. So if this is a tangent, this red line, AB, then that is perpendicular to that radius at P. Okay, let's take a look at an example here. Here we have an example that's like a problem we have seen before. We know that we have this right angle. We can once again use the Pythagorean theorem. Now this whole side over here would be the x plus 8. That's the hypotenuse. So the x plus 8 squared will equal the x squared plus the 12 squared. We reviewed the algebra that's used here. We know that x plus 8 squared means x plus 8 times x plus 8. X squared plus 12 squared is 144. Squaring on that left side, we have x times x, which is x squared, x times 8, which is 8x, 8 times x, which is another 8x, and then 8 times 8, which is 64. Collecting the like terms over there, we would have x squared plus 16x's plus 64 equals x squared plus 144. Now to solve that one, I can see that I could subtract an x squared on both sides. I can also then, after I've done that, subtract a 64. And then I simply divide by 16. I end up with x equals 5. And then if I want to find the radius of circle C, well, the radius of circle C would be that 5. Let's talk about when we have two tangents to the same circle. If we have two tangents that are common external tangents to the same circle, then they have to be congruent to each other. They're equal. So r to s will equal t to s. Let's take a look at a problem or two like that. Here's an example of two tangents to the same circle from the same point. So I know these two are congruent. Two tangents are congruent or equal. When I set up my equation, 3x plus 4 will equal 28. This one's relatively routine to solve. We subtract the 4. We divide by 3. Let's try another example of this type. Once again, in this problem, I have two tangents to the same circle from the same point, so they will be congruent. When I set those equal to each other, x squared minus 12 equals 24. This one I'm going to solve using square roots. Solve using square roots is a technique you learned in Algebra 1 that we reviewed in the first week of this chapter. And to do that, I'll add 12 on both sides. That leaves me with x squared equals 36. To finish it, I take the square root of both sides, and we end up with two algebraic answers. We end up with x equals positive 6 and x equals negative 6. This time, both will work. And I know both will work because when I check, if I put negative 6 squared minus 12, that's 36 minus 12, which is 24. If I put positive 6 squared minus 12, that is also 36 minus 12, which is 24. So both check, both work. And once again, you must box your answers, or it is wrong, because we'll have no idea if you mean them to be solutions or not. This one we have secant segments and tangent segments. Now we've already talked about secant segments in this chapter. For a secant segment, remember the pattern was we take outside times whole length. For a tangent segment, we take outside times outside. And that's simply because on a tangent segment, the whole length and the outside are both the same. Let's take a look at a problem like this. Okay, so you can see that we do have a secant segment. The one that I've highlighted here in yellow is a secant segment. For a secant segment, we're going to take outside times whole length. Now this whole length right here will be if we add the x plus the 8. So for that yellow one, I'm going to be taking x times x plus 8. Now for the tangent segment, we take outside times outside. So for that tangent segment, I'm just going to take 16 times 16. And that is what we need to solve. Let's carry out the algebra. We'll distribute the x squared plus 8x. 16 times 16 is 256. To solve this, we have to move the 256 over, so it's set equal to 0. So that will be by subtracting x squared plus 8x then minus 256 equals 0. And on this one, because the numbers are so large and I cannot see easily how to factor it, we're going to use the quadratic formula. Recall that the quadratic formula is x equals negative b plus or minus the square root b squared minus 4ac all over 2a. And yes, you do have to know that. So in the problem that we're working with, the a is equal to 1, the b is equal to 8, and the c is equal to negative 256. Putting that into our quadratic formula, we have x equals negative 8 plus or minus the square root, and then 8 squared minus 4 times 1 times negative 256, and that entire thing, including the negative b, divided by 2 times 1. And as you've seen when I reviewed these problems before, I like to work out what's beneath the radical sign, beneath that square root sign. So I have x equals negative 8 plus or minus the square root and beneath that square root sign I have $1,088, all divided by 2 times 1, which is 2. Okay, and now it's time to split that into two parts. One part uses the minus sign. X equals negative 8 minus the square root of 1,088, all divided by 2. The other uses the plus sign. X equals negative 8 plus the square root of 1,088, all over 2. Let's see what we get for each of those. For the top one, I end up with x equals negative 20.49. For the bottom one, I end up with x equals $12.49. In this particular problem, it would not make sense for the x to be negative. Can't have a negative length. So the only one that is an answer, the only one that we box is this one. And again, you must box your answers. So don't forget that. Let's try another of these. So in this problem, it looks like we have another secant segment and tangent segment. In our plan, we take the outside times the whole length for the secant segment, and for the tangent, we take the outside times the outside. So for this secant segment right here, the one I've highlighted in blue, this whole length would be if we add the x plus the 5. So I'm going to take the 5 on the outside times x plus 5. And for the tangent segment, the outside is 7. Now comes the algebra. 5 times x is 5x. 5 times 5 is 25. 7 times 7 is 49. This one's pretty easy to solve. We subtract the 25. 5x would equal 24. we divide by 5, x would be 4.8. Secant segments, outside times whole, tangent segments, outside times outside. Here's another one of these. Okay, so it appears we have that same situation. One is a secant segment. One is a tangent segment. For the secant, we're going to take the outside times the whole length. For the tangent, we're going to take the outside times the outside. For this secant segment, the top one here, the whole length would be x plus 10. So I'm taking x times x plus 10. For the tangent segment, 12 times 12. Distributing the x, I have x squared plus 10x. 12 times 12, 144. Subtracting the 144 to get it set equal to 0. And once again, let's use the quadratic formula. In our problem, the a is 1, the b is 10, and the c is negative 144. Putting that into our formula, we'd have x equals negative b plus or minus the square root b squared minus 4 times a times c. All of that, including the negative b, divided by 2 times the a. And as you've seen before, I do like to work out what's beneath that radical sign first. So I have negative 10 plus or minus the square root. And beneath there, I get 10 squared minus 4 times 1 times negative 144, 676, all divided by 2. Now I'll split it into the two parts, one using the negative, x equals negative 10 minus the square root, 676, all over 2. The other using the positive, x equals negative 10 plus the square root, 676, all over 2. I want to remind you that when you put these in your calculator, it's important to enclose the whole top in a parenthesis. If we do that for this top one, we end up with, rounding to the nearest tenth this time, tenth means only one decimal place, we end up with x equals negative 18. The bottom one we end up with x equals 8. Now, once again, in this problem, x cannot be negative, lengths can't be negative, so we would box only this one. And you must box your answers. Or it will unfortunately have to be counted wrong. Let's try one more example, and then I'll leave you to your practice. So here we have that exact same situation that we've been dealing with, the secant segment and the tangent segment. For the secant segment, right here, we know that we need that whole length. This whole length here would be x plus 14. We know that we will take the outside times the whole length. For the tangent segment, we know we take the outside times the outside. Distributing, we get x squared plus 14x. 15 times 15 is 225. We must set it equal to 0 to solve it. X squared plus 14x minus 225 equals 0. This one I cannot see how to factor quickly, so we're going to go ahead and put it into the quadratic formula. A is 1, B is 14, C is negative 225. So x will equal negative b plus or minus square root b squared minus 4 times a times c. And that entire thing, including the negative b, divided by 2 times the a. Beneath that square root sign this time, I end up with 1,096. Splitting it now into its two parts. Using the negative, we would have negative 14 minus the square root of 1,096. Using the plus, negative 14 plus the square root of 1,096. Again, when you put it into your calculator, do not forget to close the whole top in its own group of parentheses, because otherwise the calculator will not know which part is on the top and which part is on the bottom. We're going to the nearest tenth again, which is 1 decimal place. Using the negative sign, we get x equals negative 23.6. Using the positive sign, we get x equals 9.6. In this problem, once again, we couldn't use the negative because a distance can't be negative, a length of a segment. So we would only box this one. And do not forget, you must box your answers. Now, I hope that helped. I did a number of those with the quadratic formula because that will show up and you will have to be able to use it. Good luck on it. Remember the help times that are available.